Any question?
Exercise anti-commutation.
Yes.
Then it's coming 2 times.
2 times?
Because from Bn Cn product, from that we often delta x by minus n.
BMC get delta m plus n0.
When I was checking this, I got Bn times Cn, that gives me a computation of delta means this time, and from the other term Cn, Bn comes.
No, that shouldn't happen, because the point is that the BM is an integral like this. Okay? Cn will be, say, an integral like this. So BM Cn will be some control arranged in this way. This is B, this is C. Okay? Whereas the other way will be the B control inside and the C control outside. Okay. So the commutator means that what happens when you try to take the B control to be inside C. So there is one residue that you have to pick up. So it's not that then the contribution is doubled. So this anti-commutator, normally it would have been commutator, but these are anti-commutating, right? That's why anti-commutator. So it's basically the contour integral of the B around a point in C is what to calculate first, and then we integrate over the C position.
So means it will be not like close control dz close control theta, not like that.
Yeah, so let's see. So B will be z to the power n plus 1 dz, right?
Yes, sir.
Times integral w to the n plus n
Minus 2.
minus 1
So minus 2.
minus 2 dw cw, right? Okay. And then the other. So what you do is that as you pass this contour through W, because you have to find a difference between this arrangement and this arrangement, right?
Okay.
So as you pass this contour through W, you pick up a pole because ZCW has a 1 over Z minus 1. Right? So the result will be integral W to the n plus 1, W to the n minus 2, CW. Sorry, no CW because they got 1 over Z minus 1. Right? So this is the only integral that will be left. Because you are picking up the pole from that, and then when the contour has passed through, that's this one which it cancels.
So can I show what I have done?
Okay.
Taking in this fashion, I just define Z and W as U be Z plus W and Z minus W to do the integration.
Yeah.
I just found out the Jacobian that is being half done.
So you shouldn't have to change. We will see it later. You don't have to change. You shouldn't have to change variable because you are just doing the Z integral around W, right? So you can pick up the pole at Z equal to W. So you just set Z equal to W. Right? So if you look so carefully, you shouldn't get a Jacobian from this end of idea because you are keeping W fixed and doing the Z integral, right? Because you think of the W control being fixed and the Z integral once outside, once inside. Okay, and the difference will be basically the rest.
Then
Any other question? Okay. So yesterday we introduced the notion of BPZ conjugate. So let me. So I guess if phi of 0 on the matrix is the state phi, then our definition of the conjugate state, BPZ conjugate state phi, is 0 phi of phi. Okay. And one important point to note is that this doesn't involve any complex conjugation. Okay, so if you multiply this phi by some complex number, the corresponding BPZ conjugate will be multiplied by the same complex number, not the complex conjugate of that complex number. Okay, so in that sense, it differs from the standard definition of conjugation in quantum mechanics, okay, where you also have complex conjugation. Okay. So now suppose phi n is a basis state in the Hilbert space. In the Hilbert space. Now, normally in a Hilbert space, one would like to choose orthonormal basis, okay, in the sense that phi n would be delta m, and this would be the choice of orthonormal basis. Okay. However, in this case, it is not possible if you want to choose phi n's to be states of definite host number. Okay. And the reason is that imagine that the phi n has host number g. Suppose it has host number, let's not use g, let's say host number k. Then this is 0 unless k is equal to 3. Okay? Because the total host number is to add up to 6. So in a generic host number sector, okay, we cannot choose phi's satisfying this. Okay, and in fact, even in the host number 3 sector, you cannot do it because as you will see, there it will be anticipated. This program. So what one does is to define, if you want to choose say some basis, okay, and use complete test relations and so on, one introduces a new set of basis states, call it phi n c, and these by definition you choose it so that this is equal to delta m. Okay, so this is the definition of phi n c. And one can also introduce a corresponding operator. So one can write phi n c as I dot phi n c of 0. Okay, so just like you can pair states, you can also pair operators. Okay, but the important point is that you don't pair operators with itself. Okay, and try to that way you cannot get an orthonormal basis. So what you have to do is to introduce different basis states for the original for the bra and the k's. Now suppose we started with phi n c, phi n. So this you know, this we have taken to be delta m n. So let's try to manipulate this to see if we can bring phi n to the left and phi n c to the right. So this can be written as I dot phi n c of 0, phi n of 0. Okay, because by definition phi n c is the operator that satisfies that the graph phi n c is the vacuum times I dot phi n c, and this by definition is phi n 0 on 0. That's the way we make the state operator correspondence. But now what you can do is use the fact that SL2C is a symmetry of the sphere correlation function. So you can explicitly make an SL2C transformation of this, and we will make the SL2C transformation by the transformation I. Okay, let me remind you that I of z, this function is minus 1 over z. Right? This is certainly an SL2C transformation. So what we can write by using SL2C invariance, we can write this I dot n c 0 I dot phi n 0. But this is just identity. Right? If you apply z goes to minus 1 over z and then again take z to minus 1 over z, you come back to z. So this is just phi n c of 0 I dot phi n of 0. And now if you want to try to write this and back as an inner product, okay, you have to bring it on this side and this on the other side. Okay. Which, okay, I mean, let me write it this way. So I should see, it's understood that all of these are radially ordered. Right? Inside a correlation whenever you are taking a matrix element. Okay, whenever you are thinking of a matrix element, it's always radial order. Okay. So from this point itself, I should have written it radial ordering. So here, of course, radial ordering is the same as the usual ordering. But when I apply I again, okay, the ordering actually changes, right? Because this now has larger argument, right? This is infinity, this is 0. Okay, so it's already radial order. I am not just writing this. However, there is one subtle point, and that is that if phi n carries host number g, or host number n, k, if it carries host number k, then this is Grassmann even for k even and Grassmann odd for k odd. Okay, because hosts are anti-coupling. Okay, so if you want a host number 3 operator, for example, you need 3 C's, okay, or 4 C's and 1 B. Okay, always an odd number of anti-coupling operators. So the Grassmannality depends on the k, okay, and it's Grassmann odd. Grassmann odd if k is odd, and even if k is even. Which means that when you actually try to change the order, this is times minus 1 to the k. Okay, or I can write the minus 1 to the power 6 times k times 6 minus k, but that's the same as minus 1 to the k. Because you have to exchange the positions. Is this clear? Okay, so you think of this as a time ordering, okay, there is a radial ordering sitting here. Okay. But when you say time ordered or radial order of this, right, when you actually want to change the ordering, if it's formulaic, you put an extra minus sign. Right, and that's this minus sign. So this is then minus 1 to the k times phi n c. Okay. So what this says is that if you take this inner product and if you want to switch the inner product between phi n and phi n c, okay, you pick up a factor of minus 1 to the k. So it's not always even, okay. For odd host numbers, it's odd.
Say minus 1 to the k times 6 minus k.
Yeah, but minus 1 to the k times 6 is just even, right? And minus 1 to the k square is the same as k. So it's minus 1. So if k is even, then this is even. If k is odd, this is odd. So this is one of the signs that you should keep track of. Okay.
When you went from this I to this I square, this
yes.
You won't have to change the ordering because by radial ordering.
Yes. So let me write it this way. Here is radial ordering, right? Whenever you have a matrix element, I write the radial ordering.
So write it as R of this.
I write the radial ordering. Okay. Here I write as radial ordering.
Oh, okay, very good.
But radial ordering means that you have to switch the order. But as you are switching the order, you have to also pick up a minus sign if they are anti-converter. Right? It's like radial ordering or time ordering of psi of x1 times psi of x2. If x1 naught is other than if x1 naught is less than x2 naught, you have to switch the order. But it's minus psi of x2 naught times psi of x1. Right? So that minus sign has to be always kept track of. So inside radial ordering, you don't put the minus sign, but when you actually write it in this reverse order, you have to pick up a minus sign. Right? And that's this minus of the k. Is this okay? Okay. So let me divide it again. If you have time order of psi of x1, psi of x2, right? That is minus time order psi of x2, psi of x1. It doesn't matter what the argument of x1 and x2 are. Okay. Whenever you write it in the opposite order, okay, you put a minus sign. Right? So that if your ordering is actually have to be reversed, right? You keep track of the minus sign when you actually write it in the opposite order. So that's this minus 1 to the k. Okay. So let's also write down a complete test relation because that often you need to use. So given that there is a issue with sign, right, when you switch ordering, let's try to see what is the statement of completeness, right? Given a basis phi n and phi n C, which is written this way. What is completeness? So identity. Okay, and the claim is that the completeness relation takes the form of how do you verify it? Okay, we apply identity on arbitrary state. And let's take an arbitrary state to be phi m. As long as you can show that identity acting on phi m gives you phi m for every phi m, we are done, right? So this is the left hand side. The right hand side is phi n times phi n c phi m. Okay, this is what we are trying to check. Now phi n c phi m in the way we have normalized is delta n m. And that's the way we have chosen our phi n c. Okay, it's here. So this is delta n m. And so this gives you back phi. Because we need to see that this operator acts as identity on phi m. Okay, and because phi m is completely arbitrary, it's any choice of basis state, this operator is indeed identity operator. Okay. But the other way is not true. Okay, if you have taken phi n c phi n, okay, this is not identity, you have to also put this minus onto the k factor. Okay. Because of this fact, right? On the inner product, if this is delta nm, then phi n c is not delta nm, right? That is the phase minus onto the k times delta nm. Okay, and that minus onto the k since it has to be put in the definition of the completeness. Okay, so you have to use completeness, you have to keep this in mind. Are there questions? Okay. So now let me also write down more explicitly the sign and normalizing convention that we will be using for the inner product. So I write them separately for rows that matter, but you can also combine them. So if we take this object, okay, so this is the host sector vacuum. The full vacuum is the product of the host and the matter. This you can see has correctly the correct number of host, the correct host number, right? Total host number 6, right? 3 from the holomorphic, 3 from the anti-holomorphic. Okay. These modes have also been chosen precisely in a way so that they don't give you 0 identically. Right? If you recall, if you look at the definition of the vacuum, right? What modes of C annihilate in the vacuum? Okay, you will find that C1, C0, and C minus 1 doesn't annihilate the vacuum. Okay, C2 onwards will start annihilating the vacuum. So it neither annihilates the vacuum on this side nor annihilates the vacuum on this side. Okay. So this has a chance of being non-zero, and this will normalize to 1. Okay, this is a convention. Okay, I could have normalized to -1, then some other minus signs have to be changed in this. Now I will leave the exercise to check that this basically means the following. So the point is that for this correlation function, the z dependence is already fixed by conformal invariance, right? There is nothing else you can do. So the only thing that is undetermined is this overall normalization. Okay. And this you can fix by comparing with this. Okay. So the way you can do it is the following. So suppose you take z3 equal to 0. Okay. Then if you look at the mode expansion of C, you will find that if you C of 0, C bar 0 on the vacuum, this gives you C1, C1 bar on the vacuum. Okay. You take a look at the mode expansion of C, okay, and you will find that at z equal to 0, either the power of z goes to 0 or the particular mode C2, C3, etc. they are by construction and at the vacuum. Okay. So this C1, C1 bar element. Then we start Taylor series expanding these around z2 equal to 0 and these around z1 equal to 0. Okay, and in the Taylor series expansion, you basically pick up coefficients of C0, C0 bar and C minus 1, C minus 1 bar. And by comparing that with what we have here explicitly, you can show that this from this you can get here, or reverse you can go from here to here. Because the only thing that is undetermined here is overall normalization. You could fix that by comparing it. So these two are equivalent. Okay, I can write this. Again, only for the case. Now for matter, we use the following normalization convention. Imagine that we have a correlation function of this kind. So the z dependence we have already seen earlier. Okay, is our form zi minus zj equal to ki over kj. Okay, product. Okay, this you cannot do anything about. This is fixed by conformal dimensions of. Well, it's not fixed by conformal dimension, but the correlation function itself has this particular z dependence. What is up to you is to fix the overall normalization. Okay. And that overall normalization is fixed to 2 pi to the d plus 1 delta d plus 1 sum over I. Okay, where d plus 1 is the total dimension of the space time, non-compact part of the space time. Now, notice that this is different from saying that the matter sector vacuum is normalized to 1. Right? Because if you set, for example, all the ki's to 0, then you will get the normalization of the matter sector vacuum. The right hand side, this will of course be 1, because all the ki's are 0. But this will diverge. 2 pi to the d plus 1, delta d plus 1, 0. Right? So, this normalization that we have chosen is somewhat of a singular normalization. Okay. But it's necessary, and the physical reason for this is the following. Right? If you look at k equal to 0, at ki equal to 0, right hand side is 2 pi to the d plus 1 delta d plus 1 of 0. Right? But what is it physically? Right? I mean, if you recall how this kind of delta functions come, this is nothing but a volume of space time. Okay, so in particular, if we assume that the space time has a finite volume, like V, right, say length L on each side, then this regulated, once you regularize this, right, this results in a volume of space time. Okay. So basically, what it says is that you are normalizing the vacuum not equal to 1 in a matter sector, but a volume of space time in the matter sector. Right? That is the standard convention that one also uses for quantum field theories.
So, in this choice of this normalization,
yes,
the fact that doesn't depend on n, is there something not? I mean, I equal goes to 1 to n.
Yeah. So this is. I mean, it depends on n only from this.
Yeah. So is there something non-trivial to show there, or in is it obvious that there is no?
No. Yeah. There is something non-trivial to show. Is this structure doesn't follow necessarily from conformal invariance, right? For a 3-point function, it would follow from conformal invariance. So I could have written this statement for n equal to 3.
Yes.
Right? That would have fixed the normalization anywhere.
Yes.
Right? And then for the fact that this formula holds for general n, that is something non-trivial because you have to. I mean, actually, compute the correlation function.
Yeah. So those products, and there is also no additional n dependence.
Exactly.
That's
exactly. Right. So I could have, for stating the normalization, I could have just written plus 3.
Oh, yeah. But that also has this non-trivial effect that once that is chosen for n, the statement continues.
Exactly. Once that is chosen, then for n, this is true. Because we don't have any further choice of fixing the normalization.
And it does not induce any new factors.
Exactly. Yeah. So is this clear? Yeah. So this is the way we will normalize the matter sector, because if we are normalized 0, 0 to be equal to 1, right, then there is difficult to write down something like this, right? Because then for all the ti is equal to 0, this is divergent. Okay? Delta of 0, right? So how can 1 be equal to some divergent result, right? So this is the only way you can make sense of the normalization in the matter sector is by writing the normalization this way. Okay? And intuitively you can think of this as this means that if the matter sector vacuum is normalized by the volume of space time. Okay? Because delta d plus 1 of 0 times 2 pi 3 d plus 1 is indeed the regular volume of space time. And sign conventions for now. Now, what I am going to do is to turn to a general amplitude, okay, n point G loop amplitude, and try to see how to write down an expression for such an amplitude in string theory. So, general expression for G loop n point. And what I'll do is to write down the result but not give the derivation. Okay, in principle one can derive this. Okay. Starting from say Polyakov path integral, where you start with the integration over the worldsheet metric, and then you gauge fix, and then you introduce hosts, and then eventually get to this. So what I'll do is I'll write down the result, okay, and then I'll check various consistency conditions. Okay. And in that process, I'll also write down a generalization of the usual Polyakov amplitude for off-shell amplitudes. Okay, and we'll see that the way we write down off-shell amplitudes is very similar to the way we write down on-shell amplitudes. So there is not that much you have to do extra to understand off-shell amplitudes if you understand the on-shell amplitudes. Okay, so we'll treat all and off-shell amplitudes intersection. So let me first write down schematically how it should look like. Okay. So for the on-shell amplitude, the way it will look like is an integration over something I'll call MGN. This is the moduli space. Moduli space of genus G Riemann surface with n punctures. Punctures in this notation will be just some odd points on the Riemann surface. Genus is the number of angles. So sphere has genus 0, torus has genus 1, double torus has genus 2, and so on. Now, what is the meaning of a? Okay, so first let's forget about punctures. Okay, what is the meaning of moduli space of genus C Riemann surface? So a Riemann surface As I said, it's a two-dimensional surface, but we will think of this as a one-dimensional complex manifold. Okay, not a two-dimensional real manifold, but a one-dimensional complex manifold. And in a manifold, you know that the manifold is characterized by its transition functions. Right? You cover the manifold by local coordinate patches, local charts, and then you specify the transition function that takes you from one manifold to another manifold. Right? As a topological characteristic, that's all unique. Right? We will not need to worry about the making at this stage. Now, the difference between the real and complex manifold is that in real manifold, you allow the transition functions to be arbitrary real functions, whereas in a complex manifold, the transition functions are holomorphic functions. Okay, locally on that overlap, the coordinate system in one is a holomorphic function of the coordinates of the other. And two manifolds will be called the same if by making a redefinition of coordinates you can make them the same. Okay, if you can make all the transition functions the same by just redefining your coordinates in different patches, then the manifolds will be declared to be the same. So different Riemann surfaces are different complex manifolds. Okay, which means that when you say two Riemann surfaces are different, that it's impossible to make a coordinate transformation on local coordinate charts. Okay, that takes you the transition functions of one to the transition function of the other. This is the definition of Riemann surface. Okay, inequivalent Riemann surface.
Transition function of one to the other means from here to here and here to here.
Yeah, now imagine that you have a Riemann surface which is a surface which is covered by various coordinate charts, right? So the specification of Riemann surface tells us you choose some complex coordinates on each and specify how they are related. Now, so different overlap functions a priori gives different Riemann surfaces. Okay? The Riemann surface is characterized by overlap functions. But now imagine that we have two such Riemann surfaces with apparently different overlap functions. Okay? But you make the overlap functions here to be the same as the overlap functions here by simply changing the coordinate system on one of the coordinate charts, right? Or two of the coordinate charts. Then they will be declared as equivalent. Right? They look different because the coordinate system that you have chosen is different, right? But they are equivalent as a complex manifold. Okay, so the inequivalent Riemann surface means that Riemann surfaces follow this cannot be done. You cannot simply go from that. You cannot make the transition functions one to the other, okay, by simply changing coordinates. Okay, we'll try to make it more specific later when you choose appropriate coordinate charts. But this is the meaning of different Riemann surfaces, that surfaces which are inequivalent as complex manifold. Now, two surfaces which are inequivalent as complex manifold can still be the same as real manifold. Okay? Because even though you cannot make an analytic change of coordinates that makes the transition function the same, if you allow real analytic change of coordinates, if you don't require holomorphism, okay, you can allow arbitrary real coordinate change, then you may still be able to make the transition function equal. Okay? So, Riemann surfaces are inequivalent complex surfaces, right? You are not claiming that two different Riemann surfaces cannot be made to look the same by a real change of coordinates, but two different Riemann surfaces shouldn't look the same under a complex, under a analytic change of coordinates on the coordinates. Okay, and in fact, one can show in general that in two dimensions, once you fix a genus, all surfaces are equivalent as a real surface, as a real manifold. Okay, basically you can, deform any genus one surface to any other, okay, by changing the overlap function appropriately, okay, by changing the coordinates appropriately. But as complex manifold, they can be equivalent. Okay, that's the statement. And so, what is MGN? MGN means this is the set of parameters with that parameters in equivalent Riemann surfaces. Okay, different points in MGN are different Riemann surfaces which cannot be made in, which cannot be mapped into each other by simply change of coordinates. Is this clear? Now, N is an array feature here. Okay. N are some fixed points, so there are N fixed points on the Riemann surface. Okay. And right now just think of n, okay, as some additional mod points. Okay. So mgn is obtained by taking mg, okay, which is the moduli space of genus G Riemann surface, and then simply specifying the coordinates of n points on the Riemann surface. Okay, but later on we will see a more uniform description of mgn. Okay, where you don't distinguish the coordinates of points and the actual moduli of mg. Okay, I have treat them on the same form. Okay, right now just think of mgn as an abstract space which contains information about the moduli space of genus G Riemann surface and coordinates of n points on that Riemann surface.
So there shouldn't there be a sum over G?
Well, this is in genus G loop n point amplitude, so that's a fixed G. Yeah, eventually you have to sum over it.
Yes.
If you want all loop amplitudes, then is this? Yeah, so that is what we mean by mgn, right? So, for example, if you have a torus, right, say genus 1, 2-point amplitude, right? On the torus, you fix the modulus of the torus. Okay, there is one complex modulus that fixes the shape of the torus, and then you have to specify the coordinates of 2 points on that torus. But in fact, on torus, one of the points can be fixed anywhere by transition symmetry, because torus is invariant on transition, so that information is irrelevant. So m11, or sorry, m12, okay, 2-point function requires 2 complex coordinates. Okay, one is the modulus of the torus, the other one is the position of one of the points, keeping the other one fixed. Right? You can always take one of the points at the origin and the other point location is another coordinate. Okay, so m11, or sorry, m12 will have 2 complex coordinates. Is this clear? So let me write down in general, this has 6g minus 6 plus 2n dimensions. Okay. And this formula is valid for g greater than 2, greater than or equal to 2, g equal to 1, n greater than or equal to 1, and g equal to 0, n greater than or equal to 3. These are the only cases that will be considered. Okay, so if, for example, if you take genus 1, 2-point function, m12, you put it in this formula, okay, so 6 minus 6 is 0, and 2 times n gives you 2, right, with a, sorry, on the torus, g is 0, g is 1, sorry, so g is 1, so then you get 6 minus 6 plus 2n, okay, yeah, right, plus 2n, n is 2, okay, so n is 2, so that gives you 4 parameters. Okay. These 4 real parameters are 2 complex parameters. One is the modulus of the torus, and the other one is the complex coordinate of one of the points. Is this clear?
This formula will not be valid for g equal to 0.
It will be right for g equal to 0 as long as n is greater than or equal to 3. Okay. And as I said, those are the only cases we have to consider. Because g equal to 0, take g equal to 0, n equal to 3. Right? Then you will get the result, this is 0. Right? And you know that a sphere with 3 points has no modulus. Because those 3 points can be fixed by eccentricity transformation. Right? Sphere with 4 points start having one complex modulus. Right? And that's what you see also from this formula. So, now the question is, what is I? Okay, I should say that later on, okay, hopefully by end of this lecture, I will also try to give a more explicit way of describing the moduli space. Okay, but let me say a few words about I. So I is the integral. has to be integrated over mgn. Right? So this is a 6g minus 6 plus 2n form. Okay, that's what you can integrate on a 6g minus 6 plus 2n dimensional space. These are real coordinates. Okay, these are all, this dimension is real. Now, what is it? That's what we want to write down. Okay. But roughly, let me say at this stage that what it is that it involves a correlation function of these are the vortex operators of the n states times some post insertion, which I will describe in detail later, on sigma gn. Okay, so sigma gn is the Riemann surface of genus T with n marked points. Okay, so what the structure, the general structure is the following. Okay? You have to integrate over mgn, the moduli space of genus C Riemann surface with n punctures. The integral will have to be a 6g minus 6 plus 2n form on this moduli space, and it is constructed as a correlation function of the vortex operators that describe their external states. But this is not the full story. Okay, in this correlation function, you also have to insert some appropriate ghost operators, which I will describe in detail. And this correlation function is to be computed on the Riemann surface. Right? So as you move in mgn, right? Imagine that you go from one point on mgn to another point in mgn, the Riemann surface is going to change. Right? That's what after all mgn points in mgn level the Riemann surface. Right? Either the Riemann surface itself changes or the punctures move. Right? You go from one point to another point. So the correlation function changes, and this is what you have to integrate. So this is the general structure of genus C n-point function. Okay, and our goal will be to make this more explicit. Okay, by first saying how to parameterize mgn, and then specify how to write down this integral. Right? What is it exactly? Okay, what kind of host insertions you have to use in the integral.
So picture number is in AI now?
No, this is bosonic string. So you know picture number doesn't come in. Right? AIs are just external states. External states all of post number 2. Right? In particular, for on shell states, you take them to be C bar C here. Okay, where the I is dimension one parameter. Is this clear? Now let's see what will happen if you take the AIs to be off shell. Okay. What do you mean by take the AIs to be off shell? When the AIs are not of this kind. Yeah, they are some general operators which are not dimension 0 primaries. Then what I have written is not complete. It's not complete because now the correlation function will depend on the local coordinate system in which you insert these AIs. And as we saw last time, just saying that we will insert AIs is not enough. You have to specify which local coordinate system you use to insert AIs. Okay? So around each function now, we have to choose some coordinate system, and then say that we will insert AIs with that particular choice of coordinate system, taking a metric in those coordinate systems to be dwi mod square. Okay? So the integral, okay, even without knowing anything about this host insertion, we know from the general structure the integral will now not only depend on sigma gn, okay, the particular Riemann surface on which you are working on, but also what kind of local coordinates you have chosen around the punctures. Is that clear? And that choice, of course, is encoded in a set of functions. Right? For every point, every puncture, you have a function. Right? So there is a infinite class of choices. Right? What kind of local coordinate system you can choose, because you can choose any function that you like near the function. So now the structure is the following. So let's introduce a space PGN.
So, like last time, couldn't we just write it in terms of those local coordinates?
Yes, you could.
Then
So I write as f dot ai. Right? Fi dot ai. Around each coordinate system, you choose some local coordinates, which is the overall coordinate system by some function.
then there will be no other function.
Yeah, but those functions will depend on those functions. Right? I could change those functions. Right? And the result will be different. Okay. So let me try to describe in abstract terms what is happening and what is the best way to think of this. So we introduce a new space PGN, which is actually an infinite dimensional space. So this is a fiber bundle with base MGN and fiber containing information about possible choice of local coordinates. So fiber is infinite dimensional. Okay, for any point in MGN, for any particular surface sigma gn, okay, the fiber direction labels all possible choices of local coordinates, which means the fiber is characterized by n different functions. Okay, because for every function you can choose a function. Okay, so that's the fiber direction. So that's the reason why this space is infinite dimensional. Okay, but nevertheless, it's not conceptually, it's not hard to understand what this space is.
So it is local coordinates about the punctures, not
About the punctures, exactly. Yeah. Not, as you saw that the result will not depend on the choice of coordinate system at a generic one. It will only depend on the choice of coordinate system around the punctures.
So do we need information around about all the coordinate systems around all the punctures, because you have fixed one of the punctures in torus?
On the torus, but even then, the local choice of coordinate system around that will be important. Right? For example, if you take a 3-point function on the sphere, right? The coordinates are all fixed, right? There is no modulus. But nevertheless, the 3-point function, official 3-point function on the sphere, does depend on the choice of local coordinates around those 3 functions. Right? We saw yesterday that we had this f1, f2, f3, right? And the result did depend on the choice of f1, f2, f3. Right? Under SN2C it was invariant, but if you had to change, say, the definition of W1, right, which means changing F1, the result would have changed, right, for official amplitudes. So, indeed, you do need information also about the punctures which are fixed, right, by symmetries.
But Z1 is 0 at that point.
Yeah, Z1 is 0, exactly, right. But when you write a local coordinate system, right, you write Z1, Z is equal to F of W1, right. So W1 equal to 0 maps to Z1 equal to 0. So which means the f of 0 is 0. But its derivatives can be non-trivial, right? And those derivatives enter in the definition of this f dot phi that we introduced. Right? So that's the reason why the choice of local coordinates affects the official amplitude. So even if the point itself is fixed.
So isn't to see invariant of this integrand is obvious?
Well, on a sigma gn in general, there is no SN2C. Right? If you are doing it on sphere, then yes, all correlation functions on the sphere will be SN2C invariant, right? Okay, it's not obvious in the sense that you have to make sure that the host instructions are such that it transforms correctly under SN2C, right? And that we have not told you anything about how the host instructions are done, Right? Once you do this, it will become clear that if the Riemann surface has some inherent symmetry, it will be inherited by the correlation.
What is the dependence on the Riemann surface moduli? In the sense that are these fibers only related to the punctures?
Yeah, they are related to the punctures, but of course, if you change the Riemann surface, right, then it doesn't make sense to say that you are comparing, you are keeping anything, the coordinates fixed. Right? Because, see, if you change the Riemann surface, right, then there is no notion of how to relate the puncture coordinates of the original Riemann surface to the puncture coordinates of the new Riemann surface. Right? It's a new configuration altogether. So that's why that the fibers, so this is PGN, right? You think of each point in the moduli in this direction, right? It is a fixed Riemann surface. Given that Riemann surface, you have a whole class of choice of local coordinates, right? And that is the vertical direction. So this is the whole space PGN. Okay? PGN contains information about which point in MGN you are in, okay, that means which Riemann surface you are in, and also what kind of local coordinate system you have chosen. Now, when you try to define an off-shell amplitude, okay, of course you choose some specific local coordinates. Okay? The result does depend on a choice, but after all, defining the off-shell amplitude will require choosing some coordinate system. Okay? Just like yesterday you saw on the sphere, if you want to define the off-shell amplitude of 3 points, you have to choose this function say for f2 and f3, and only then you will get a definite answer. So in this language, the choice of a local coordinate system, okay, which is required for defining the off-shell amplitude, corresponds to choice of a section. Okay. Once you give a section of the fiber bundle, that basically means that for every point in MGN you have some particular choice of point on the fiber direction, right? And a particular choice of point in the fiber direction corresponds to a very specific choice of local coordinate system on the manifold. Okay? A specific point means that you have that basically says that you have chosen all the functions. Okay? Different function, if any of the functions differ, it will be different. Okay? And the off-shell amplitude should be different. Is this clear? So this is the general picture that the space of all possible local coordinates and all possible Riemann surfaces is this big space PGN. Okay? And in defining an off-shell amplitude, you have to make a choice of a particular section of this fiber.
So this is a statement at the level of the amplitude. Like if I am considered only with the integral, I have always fixed on a point on the MGN.
Integral.
Just for the integrand, I am always on a point on the MGN line.
And also on the point on the PGN line, because to compute the integrand, you have to fix the local coordinates, right? Because if you change the local coordinates, these will change, and the integrand will change. So to define the integrand, you have to fix both the point on MGN as well as the point on PGN. Okay? And then when you want to define the integral over MGN. Okay? See, you are not going to define the integration over PGN. That's an infinite dimensional space, right? So off-shell amplitude will be described still by an integral on MGN. Right? But as you move in MGN, your local coordinate system has to be chosen for every point on MGN, right? Because there are different Riemann surface, and you have to choose the corresponding local coordinates at the punctures for that Riemann surface. Okay? So that choice is encoded in this section.
So the final answer, the amplitude, is for a specific section.
Exactly. The final answer for the integral will depend on the choice of section. Okay? Off-shell amplitude, okay, will depend on the choice of section. Okay, and of course one of our goals will be to show that anything physical that we compute from the off-shell amplitudes should be independent of the choice of section. Right? Otherwise, it doesn't make sense. Okay, but off-shell amplitudes will depend on the choice of section.
So means if we choose a different section, then those will be different functions.
Those will be different functions, exactly. But then the physical quantities that we are extracting from those functions should agree.
Yes.
Right? Okay, let me just make some technical points. So first point that we have said that the fiber direction these are labeled by choice of local coordinates, right? Okay, or equivalently, we can say if you have a fixed coordinate system z on the Riemann surface, then it's choice of the functions that relate the w's to z's. Okay? That's what we mean by choice of local coordinates. Right? Just like yesterday, we had a global coordinate of the sphere which we call z, and then choice of local coordinate w basically means specifying the function that relates z to w. But this is not totally correct. Okay? There is a qualification has to be added. This is the choice of local coordinates up to phase rotation. Of WX. Which means that a choice WA and it to be I alpha A times WA are taken to be equivalent. Pardon?
This is an extra Evans method.
Well, yeah, this is an extra Evans method each function. Okay, that you don't. So suppose you have chosen one WA, okay, and another WA which are related by phase rotation. Right? If in terms of functions, okay, suppose you have chosen a function f1, okay, so that z is equal to f1 of w1, and suppose you have chosen another function f1 tilde of w1, and the f1 and f1 tilde are related by the relation that f1 of w1 is equal to f1 tilde of which the I alpha 1 times w1. Then we don't think of f1 and f1 tilde as different functions. Okay, we think of them as the same function. Okay, the same choice of local coordinates. We don't represent them by as different points on the fiber direction. We represent them as same points on the fiber direction. Is this point clear?
What is the? I mean, is it obvious that this is? I mean, why are we saying?
Yeah. Okay. I mean, first you can ask why is it needed?
Yes, what? Yeah.
Okay. It is needed because what you can show that if you don't make this identification, okay, it is not possible to find a global section. Okay. So you cannot define official amplitudes because to define official amplitude you need a section, right? And you cannot find a section. Because what you will find is there are closed cards in the moduli space, and as you go along the closed card, right, the original choice of section, the original choice of function will come back to itself, but up to this kind of transformation typically. You can never take these alphas to be 0.
Because of this choice of this metric dw mod square, right? That's why you have this choice of.
Well, that's one way of saying this. But suppose you didn't draw anything about the metric at all. Okay? You just want to see if it is possible to choose a section of this space, okay, which means that for every point in the moduli space you want to choose some local coordinates, right, and you want it to be continuous. Right? You don't want it to jump suddenly, right? As you move from one point to the neighboring point, you don't want the thing to jump. Then you can show that it's impossible to find a section which has the property that it's continuous, and as on a closed curve it comes back to the original choice. What you can do at base is that it comes back to the original choice up to a transformation of this kind, okay, where the local choice, local coordinate has gotten rotated by some phase. Okay, then you cannot direct a frame. It's like choosing local coordinate is like directing a frame, right? At every point, right? And what you find is because of the curvature of the Riemann surface, that as you go around a closed card in the moduli space, the frame gets rotated. Okay, it's impossible to come back to the original frame.
So in this diagram, can we see this this phase rotation, how it will remain the same? In this diagram, can we see?
Oh, in this diagram, you are just saying that this fiber direction is defined as the state of local coordinate choice up to this equivalence.
Oh,
Okay, But now the point is that if this is really true, right, if we say that the fiber direction has to be identified, we better make sure that the integrand is not affected by this phase rotation, right? Because we had argued earlier the integrand depends on the choice of the local coordinates. Right? For a general optional amplitude, the integrand depends on the choice of local coordinates, right? Now if you are saying that W and equally I alpha times W gives the same local coordinate, they have to be identified. We better make sure first that the integrand is the same, right? Because if the integrand changes, as you change from W1 to W to the I alpha times W1, then it doesn't make sense to say that they are the same. Okay? You cannot make them identify them because then the integrand is not a well-defined function of the fiber coordinates, right? You again are back to the same problem that you cannot integrate. Okay? So you have to ensure that the integrand doesn't change when you take a local coordinate system and just put a phase on it. Okay? Change it by multiplying by a phase. And this requires that we restrict the optional states not to general optional states but to certain subclass. This requires that we restrict optional states to satisfy Now this condition is easy to understand, right? Because what is it saying? It is invariant under L0 minus L0 bar. Right? How does it help? If the state is invariant under L0 plus L0 bar, right, then if you change coordinate from W to the I alpha times W, right, how does it act on the state? It acts by e to the I alpha times L0 minus L0 bar, right? Because a change of phase of a local coordinate, when you apply on the state, it goes e to the I alpha times L0, right? So a phase rotation will act as e to the I alpha times L0 minus L0 bar, and as long as the state is annihilated by L0 minus L0 bar, a phase rotation will not change the optional amplitude, will not change the integrand, right? And that is the reason why I have to impose this condition. Okay? That if we are saying that we can identify local coordinates, we can only define local coordinates up to phase. Right? Then those kinds of choice for local coordinates can only be used to define optional amplitude if you also impose this condition. Okay. The meaning of this condition will be clear later. Okay, but it turns out that we also have to impose this condition on the optional states. Okay, so for now let's assume that we impose these conditions and then proceed and see what we get.
0 minus L0 bar also follows physically, right? And there is no special point on the closed plane.
L0 minus L0 bar. Yeah, you can think of it that way, but that's a symmetry. Right? Now the question is whether you want to mod out by a symmetry or not in defining optional amplitudes. You could have imagined that it's a transition symmetry, right? But you don't have to mod out by a symmetry necessarily. Right? Because the physical closed string states are of course only described by on-shell states. Right? Those are annihilated not only by L0 minus L0 bar but also by L0 plus L0 bar. Right? When you are trying to define off-shell states, you are trying to relax on these constants as much as possible.
Yeah, but this is like a statement that no point on the closed string is special, right? I mean,
that is true. But similarly, L0 plus L0 bar, right, is a statement that the Watership theory is conformal invariant, right? That conformal transformation should leave the vertex of orders unchanged. Yes, just like this is, if you think of this as a cylinder, this is transition symmetry along the circle. Right? L0 plus L0 bar is a transition symmetry along the direction of the cylinder, right? Now you could have said that you impose both conditions, right? L0 plus L0 bar and L0 minus L0 bar. But what we are doing here is that we are relaxing the first condition. L0 plus L0 bar is not 0 for on-shell states. L0 minus L0 bar is taken to be 0. The point is, you can see that if L0 plus L0 bar had been taken to 0, then what we did last time wouldn't make sense, because you couldn't have introduced infinite number of intermediate states, maintaining having a complete set of states, right? So you couldn't give a field theory interpretation if you had from the beginning said that we also impose the L0 plus L0 by equal to 0 condition.
The denominator would have vanished.
Pardon?
The denominator would have vanished in this case.
Yeah, the denominator wouldn't have, I mean, you cannot write a complete set of basis states in which you can expand, right?
Yes, sir.
If you try to also restrict to states which are L0 plus L0 by equal to 0.
Is there any easy example in which I can see this? That there is no global section?
Well, it's a topological abstraction, so I don't know that there is an easy example, right? But it basically
But how do you know it is not more severe? How do you know it will stop at U1 and not go to...
Yeah, so this you can check in general. Okay? The abstraction comes from topological abstraction. Okay? And the topological abstraction basically prevents this phase rotation. And once you remove the phase rotation ambiguity, okay, by modding out, okay, then it is possible to choose global sections.
Where can I see this?
I think in this Weibull's string field theory construction you can probably find the global sections.
Is it possible that P0 bar doesn't automatically follow because these are not BRS invariant states?
What is not? Yeah, these are not BRS invariant states, exactly.
So the second condition and the first are not directly related.
No. It will be, I mean, you will see that this is also, the origin of this is still the same condition, that we have to identify these two different choices of local coordinates as the same choice of local coordinates, but that will become clear a little later, not immediately. Okay, this is obvious, right? That if you want the amplitude to be independent of such phase rotations, right, then you better have this condition on the offset states.
Is it possible to this additional restrictions see in that diagram, like the section is smooth or it makes a loop in that?
Yeah, it will make a loop in that, exactly. That what will happen is as you move, it's a, I mean, I have drawn this as a straight line, but moduli space is in general complicated, it has a complicated connectivity, right? So what will happen is as you move around a closed curve in this moduli space, okay, here the choice of local coordinates, what you can find that it's impossible to have a closed curve in the fiber direction. Okay? And as you move around in the moduli space, okay, what happens is if you didn't make this identification, you will somehow spiral. You will come back at a different point. Okay, that's the meaning of absence of a global section, right? That it's impossible to find a section, right, that has all the right periodicities. But this happens only after this phase shift. That if you are willing to say that the choice of F1 and F1 related by this are declared as the same choice of local coordinates, right? Then basically in the fiber direction, okay, certain directions are collapsing 2 points. Okay? These U1 directions for every function, okay, you are basically taking one particular circle direction and contracting this to a point, right? In the way we are defining PGN now. Okay, after this identification, is that the original PGN has some n circle directions, each of which have been collapsed to points. Okay, and with that, now it is possible to choose global sections.
And possibly that's what Abhishek was asking. This is the only obstruction?
Yeah, this is the only obstruction, exactly. Okay. So now, let me state the goal, what you are going to do. So first we want to find parameterization of and its tangent space. And once you have found the parameterization of PGN, you can also automatically convert this to parameterization of MGN by just collapsing the data on the local coordinates. The parameterization of PGN will contain information about both the moduli as well as the choice of local coordinates. If you just forget about the choice of local coordinates, you get a parameterization of MGN. But we will also need a parameterization of the tangent space of PGN. Okay? Because eventually you want to define forms, and for defining forms you need tangent vectors. So then the second step is to construct a P form omega P on PGN for all P with nice properties. Okay, and we will discuss what the nice properties are. And the third is that we define amplitude of our on cell by integrating omega gn or omega 6g minus 6 plus 2n over the section. Okay, and one of the properties that we will be having, of course, is that if the external states are on shell, then the results will be independent of the section. Or another way of saying this, then the omega, okay, will descend down to a form on MGN. Okay. In general, omega is not a form on MGN because omega will depend on the choice of section. But when the external states are on shell, okay, the omega 6g minus 6 plus 2n will actually descend down to a form on MGN. Right? It's independent of the choice of section. Not the whole of PGN, over a section of PGN.
Over a section.
Right? Because, yes, PGN of course is infinite dimensional. So you certainly don't want to carry out the integration over PGN. Right? We choose a section, right? The dimension is still 6g minus 6 plus 2n. Right? Because the base has 6g minus 6 plus 2n dimension. And you will carry out the integration over that section. And then the idea is that if the external states are on shell, then the integrals will be independent of choice of section. Right? Any choice of section will give the same integral. And this essentially means that omega basically can be used to construct a P form, a 6g minus 6 plus 2n form on MGN. Right? Because if you have a form that you can integrate over a section, and if all sections give the same integral, then it's like it induces a form on MGN. But this property, of course, is something you have to check. That for on shell amplitudes, the result is independent of the choice of section. Okay. So now we begin by parameterization of PGN. So let's take some sigma gn, which is a genus P Riemann surface with n functions. Now, you can easily verify that such a Riemann surface can be regarded as a collection of objects and be regarded as a collection of or as a union of first of all n disks. Do you want to be n? One around each function. Then let's see, 2g minus 2 plus 2n plus n spheres which are collected denoted by SI, I equal to 1 to 2g minus 2 plus n, each with 3 holes, and these are glued along 3g minus 3 plus 2n circles which are denoted by CS with S runs from 1 to 3g minus 3 pairwise. So I will illustrate this with some examples. Consider a sphere with 4 punctures. Okay. So we want to divide up the sphere, okay, as a union of first of all n disks, so 4 disks, one around each function. So cut out 4 disks. Okay, D1, D2, D3, D4. Okay, so disks are cut out, and then the rest of the region, okay, which is the sphere minus the 3 disks, we want to think of as a collection of 2g minus 2 plus n spheres. So 2g minus 2 plus n is in this case. So 2g minus 2 plus n will be g is 0, so minus 2 plus 4, that is 2. 2 spheres. Okay. And these will have 3 holes. Now here we have a sphere with 4 holes, right? That's not what we want. We want 2 spheres each with 3 holes. So we cut out, consider a division like this. So now you see that we have 4 disks. Then the left half has a structure of a sphere with 3 holes, right? This is one hole, this is a hole, and this is a hole. Right side is a sphere with again 3 holes. Right? So it's a collection of 2 spheres each with 3 holes and 4 disks. Right? This is what one means by saying by this technique. Okay, now let me now do a little more complicated example. Say like a genus 2 surface with 3 functions. G equal to 2. Oh, the number of circles is also fixed. let's say number of circles is supposed to be how many? So this is g equal to 0, so minus 3 plus 2n is 5, right? 2n is 8, that is 5. 5 circles, so let's look for 5 circles, 1, 2, 3, 4 and this is the 5th circle. Okay, in fact that number of circles is not independent because you basically add up, each sphere has 3 circles, right? So 3 times this, right? Each disk has 1 circle, so n, right? 3 times this plus n, and then each circle is shared by 2 components, right? So you have to divide by 2. Right? That's what this number 3g minus 3 plus 2n comes. Okay, so g equal to n equal to 2. Okay, let's try to do this. So here are say 2 functions. So the first job is to cut out disks around each function. Okay, so this is one disk, they are the disk, right? So D1, D2. And then the rest of the surface is supposed to be cut up into sphere with 3 holes. Okay, so let's try this how this can be done. So let's cut it like this. So this region, okay, is topologically a sphere with 3 holes, 1, 2, 3. Right? Otherwise it's simply connected, it's sphere. Then here I draw this. So this region is again a sphere with 3 holes, 1, 2, 3. Right? This region is simply connected, that's sphere up to these holes. Then you can put so let's count how many spheres we have. S1, S2, S3, S4. Okay, so the number of spheres is supposed to be 2g minus 2 plus n, 2g minus 2 plus n, which is genus 2, so this is 4 minus 2 plus 2, that's 4. Is that clear? Now the advantage of using spheres and disks is that there are standard coordinate systems on the spheres and disks. Right? The sphere is like a plane, right? And the disk is also like a disk, right? You can parameterize it. So let's suppose that WA are some coordinates on the disk, coordinates on DA, and ZI's are the coordinates on the side. So we don't have to like any coordinate. Okay, any coordinate system that covers the SI's, okay, not the full SI but the SI's of the holes in a one-to-one fashion, and WA's are any coordinate system that covers the disk in a one-to-one, that parameters the disk in a one-to-one fashion. Okay, what happens outside the disk is not visible here. We have to specify the relationship between the W's and the Z's on the interface. Right? If we say the transition function, okay, how the W's and the Z's are related, and how the Z's of this and Z's of these are related, that gives the complete data about the surface of the complex manifold. Okay. So in general, you have a relation like Zi equal to Fia of WA and Zi equal to some Fij of Zj on the order side. And so now the point is that if you take the collection of these functions, phi, and the collection of the functions phi g of zg, contain complete information about sigma gi. Okay, in fact, they also contain information about PGN if we take WAs as local coordinates. Is this clear? Now, of course, this information is highly redundant. Okay? This is an infinite dimensional space. Right? Fi here, a collection of all functions Fi, that is infinite dimensional space. Right? Because Fi can be anything. Okay? Similarly, Fij, okay, collection of all functions Fij is an infinite dimensional space. So, it is true that this contains complete information about sigma g, but it is highly redundant. And the redundancy is essentially encoded in the fact that you can change these functions by just redefining your coordinates z and w. Suppose you change z, instead of using the coordinate z, you use some function of z. Right? Instead of using zi, you use some function of zi. Then that will change the form of phi on the vertex. But you know that this is not a change of the Riemann surface. Right? You are just changing the coordinate system on that particular patch. So the set of these, okay, so MGN, okay, the abstract definition of MGN is that it's a collection of these functions and Fij modulo reparameterization of Zi's and W's. Okay. If you take two different sets of Fij's and Fis, okay, if they can be related to each other simply by changing the coordinates Zi and Wa, then they give the same Riemann surface. Well, it's not quite true. What I have described here is not MGN but MG. Okay, this is the modularized case of general Riemann surfaces. To get to MGN, okay, we have to put one restriction. We keep WA equal to 0 unchanged. So what does it mean? What this means is the following. Take a relationship between Z and W. Right? You have some relation. Now suppose you can change that relation by a transformation W goes to W plus A. Okay? Which as a Riemann surface, okay, when you think of it as a Riemann surface, it's perfectly arrowed coordinate. But W goes to W plus A actually moves the location of the puncture. If you are thinking of the puncture and the vortex of water being sitting at W equal to 0, then W goes to W plus A, right? Under that coordinate change, the puncture has shifted, right? So this, indeed, this gives the same Riemann surface, except that the puncture is now at a different point. So if you want to parameterize MGN and not MG, okay, then we have to mod out, you have to quotient by only those transformations which leave WA equal to 0 unchanged. Physically, what it is doing is that it's originally to get mg, you quotient it out by arbitrary parameterization. Now, what you are quotienting out by has reduced a bit because you are not allowing arbitrary parameterization. You are allowing only those reparameterizations which keeps WA equal to 0 fixed.
So we are keeping a section of PGN fixed now.
We are keeping a section of
PGN fixed now.
no, we are not talking about section at all. Okay. This is a general definition. So here it's MGN. Okay. So PGN we have basically collapsed. So this defines MGN, not PGN. If you want to define PGN, then you have to use reparameters of Z's only, not of W's. Okay. See, changing reparameters of W's is changing the local coordinates around the punctures, right? In PGN, that's a physical motion. Okay. In MGN, changing local coordinates of the punctures makes no difference. Right? Modular space doesn't know about the local coordinates of the punctures. Right? It carries no information about local coordinates. So if you want to define MGN, then you mod out by reparameterization of Zi's and W's only with the restriction that the origin is kept fixed because that's where the function is. Okay? Shifting WA equal to 0 to something else will correspond to changing the puncture from one position to another position.
So the integrated vertex operators, why do you want to keep W fixed?
Well, there will be no integrated vertex operators in this formalism.
Oh.
All vertex operators will be fixed. Okay, we will see how the integrated vertex operators eventually come about. But in this formalism, there will be no integrated vertex operator. Okay, so that's what I meant by saying that it will be a formalism that is completely symmetric in all vertices. Right? And the only vertex operator that we will ever need here is C bar CB. Right? The vertex operators which have ghost number 2, dimension 0.
And in this formalism, WA and e to the I alpha a WA equivalence is not imposed, or is it imposed?
Yes, it is imposed. Well, if you are modding out by all possible reparameters of WA,
that is
then you are automatically modding that.
So here also is the phase of Zi reparameterization.
No, phase of Zi is, well, see, Zi is any reparameterization of Zi is an equivalence in this formalism.
So that is also included.
That is also included, exactly. Right? So the only issue was the phase of W. Right? In PGN, so let me write down the definition of PGN, I think it will become clearer. So PGN will be again the same collection FIA and FIG modulo reparameterization of Zi and the reparameterization so the definition of PGN you quotient out only by a very specific kind of reparameterization which corresponds to change of phase of W. This of course leaves WA equal to 0 unchanged. So this is why PGN is much larger than MGN. Okay? In PGN you are quotienting by much less. Okay? Because you are leaving out all possible reparameterization of the W coordinates, okay? Except the phase change. Okay, MGN you are quotienting by arbitrary parameterization of W with the constraint that WA equal to 0 should go map to WA equal to 0. If you are interested in MG, not MGN, then you quotient out the arbitrary parameterization of W without this constraint. Right? Then the denominator by which you are quotienting is even bigger. So MGN has less number of dimensions. But MG will have less number of dimensions. Right? So every time you add a function, you have this additional constraint which increases the number of moduli. Okay, this will be the view of MGN that will be taken. Right? So the integration over the locations of the punctures in this language will be integration over the this space spanned by Fij and Fij modulo these transformations.
Basically, if two punctures are coming very close to each other, then maybe we should distinguish between them. But
In this formalism, there is no place where two punctures will come close to each other. Punctures will be fixed once and for all. Right? All that will be changing are these. Okay, so that is the advantage of this formalism, that punctures will never come close to each other explicitly. Okay? Then something will happen to the transition functions. Okay, it's like, see, this will essentially encode what we saw explicitly last time in the first lecture, that when two punctures are coming close to each other, we did a rescaling, right? Put them at fixed points 0 and y4, right, which are fixed, and then we converted this into an integral over lambda, right? So the two 3-point functions that we got in the product, there the punctures are all fixed, right? And the whole integral was converted to the integration over lambda, which is some abstract model, right? We'll see that coming out explicitly from this formalism, right? Instead of starting from the integrated vertex of order formalism and going backwards. Right? In this formalism, that will be the natural form in which you'll get all amplitudes. Okay? So punctures will never come close to each other.
So we are moduling out the transformations or the reparameterization which shift W equals to 0 and does not shift W.
The reparameterization should keep W equal to 0 fixed. It doesn't shift W equal to 0.
That should be included in MGN. Those reparameterizations are included.
Yeah, which means that because you are quotienting by a group which is lower, which is less, because you are not allowing these reparameterizations, right? So MGN will be bigger, right? So MGN will include and have some extra integrations, right, which should have been modeled out if you didn't have this constraint. Right? But now with this constraint, right, those are not modeled out. Right? And that's the sense in which MGN will be bigger.
Are these mark points distinguishable or?
Well, we can take them to be distinguishable for now, but eventually we will be considered them indistinguishable.
But if there's.
Well, see, what you can do is you can take them to be distinguishable from now, right? But later on, when you choose sections, right, we will only choose those sections which are completely symmetric under the extended terms.
So otherwise there will be some n factorial.
Exactly. Otherwise, you have to put an n factorial and average over sections. Exactly. Okay, but right now we are not imposing this constraint that they are distinguishable. They are indistinguishable. Right? Let them be arbitrary. Right? So at the level of EGN, right, we allow the choice of local coordinates and defined functions to be different. Is this okay? So this is abstract, okay, but we'll eventually, okay, in explicit examples, convert this abstract definition into concrete integrals, and will in particular reproduce a 4-point function. Okay. But we are not done yet. This defines the way you parameterize a moduli space. Right? Now we have to describe a way to parameterize a tangent space to this moduli space. Okay. And once we have parameters of a tangent space, you can define forms. Okay, because after all, what are forms? Right? Forms are abstract objects, but forms contract with tangent vectors are just numbers, are functions. Right? And then you can explicitly write down expressions for those functions, right, in terms of correlation functions or Riemann circles. So what we will do next time is to introduce tangent vectors to the moduli space, okay, which will be basically infinitesimal variations of these functions. Okay. Then we will see that how we can define omega p, right, which is a p form. Okay, and the way we define omega p is that we will give an explicit formula for what happens when you contract omega p with p tangent vectors, p arbitrary tangent vectors, okay, which are parameterized by changes of fn. Small f and capital F. Okay, and then we'll basically discuss that it has various nice properties, and using that eventually we'll construct the integration measure on the moduli space. And any questions?
So the variable that we are integrating is over integration d not mistake.
Well, here it's abstract. It's like integral d small f d capital F modeled out by these reparameterizations, right? But to actually do some integral, right, what you have to do is to, where parameterize small f and capital F by some parameters. Right? And as you vary those parameters,
We are integrating over this Riemann surface, this
space of Riemann surfaces,
space
right?
of Riemann surface.
And you go from one Riemann surface to another by changing these. So that looks like a very abstract definition, right? I mean, you cannot, that will be like a functional integral, right? You are doing a functional integral or modeling out by some reparameterization, right? But what you have to do is you have to parameterize these transition functions in terms of some finite number of parameters, and you eventually integrate over those parameters. Okay, so continue next week.